Hello, welcome back to Quantum Computation Explained. I'm Kadiresan. In this video, we will learn about quantum Fourier transform. In short, we call as QFT. So what is QFT? It's basically a linear transformation on quantum bits in some state transformed to another state. And it is quantum analog of the discrete Fourier transform. I'm sure most of you are aware of Fourier transform. So many people use in signal processing to transform time domain data to frequency domain data, right? It was discovered by Don Coppersmith, a well-known cryptographer from IBM. QFT has got computational advantage over fast Fourier transform. You know, fast Fourier transform itself is one of the methods of doing Fourier transform in an efficient way, and QFT has got computational advantage over it. It's more than the computational advantage. QFT is also popular because it's a part of source algorithm for factoring and computing the discrete algorithm. It's part of quantum phase estimation algorithm for estimating the eigenvalues of a unitary operator. In fact, source algorithm uses QPE. QFT is also part of algorithms for hidden subgroup problem. So QFT not only having computational advantage over FFT, it has got certain applications in quantum algorithm. I'm sure you can also come out with more applications. So now we'll try to learn about what exactly it is and how to implement in a quantum computer. So let's start with the definition of Fourier transform. So this is the definition for classical Fourier transform. And what it does, it gives the relationship of converting the input state. Suppose we are given a set of input vectors xj. After transformation, we'll get another set of vectors yk. Okay, and both can be in complex number. Both can have complex numbers. To try to understand a little better, I'm sure most of you are aware that in signal processing, suppose we are given a wave like this, and the data is given as we can say x1, x2, x3, x4, x5 like that at discrete time steps. With the help of Fourier transform, we will be able to convert this time domain data to frequency domain data. So basically what it does, it helps us to find out the frequency content in the signal. And then we'll be able to see separately two, for example, in this case, two sine waves are built into this waveform. We can find out that the amplitude will peak in that particular frequency. Yeah, okay, so here what is the definition? Now you can see the definition is almost the same, except that we will be acting on some state of qubits with the data encoded in computational basis, that is J state, okay? And after transformation, we'll get again qubit in K states, but this time it will be in Fourier basis. So what is Fourier basis? You will come to know subsequently in this video. Okay, so this transformation is something similar, we can say, except that we are going to operate on qubits. All right. So this is the definition taken from the previous slide. So now we need to understand how do we implement. For that, let us see. They're all constant, 2 pi I, but this is something we need to evaluate. So let us see how to evaluate. For that, we need to understand how J and K are really represented. Okay, so if J is a whole number and expressed in binary form, that can be written like this: J1 into 2 to the power of m. The J1 represents the most significant digit, multiplied by 2 to the power of n minus 1 if there are n digits in the given vector space. Okay, so j equal to j1 into 2 to the power of n minus 1, j2 the next most significant bit. Now you can see here 2 to the power of n minus 1 has become n minus 2. Like that, gradually the power gets reduced as we move on the right side, and finally we'll end up with 2 to the power of 0, or just multiplied by 1. This is something similar to what we do in binary, in decimal, correct? So, this is having 100, the value of this position is 100. Same thing like here. So the most significant bit for 3-digit number, it will become like 10 to the power of, I'm just putting 3 minus 1, which is 10 square, 100. So this will become 10 to the power of 3 minus 2, which is nothing but 10 to the power of 1, 4. So you can see here, there are exactly the same way we are writing, correct? So k also can be represented in this exactly the same way. But as you can see here, this expression is good as long as the numbers are whole, meaning 1, 2, 3 like that. Suppose if we have a fraction, then this expression is not good. So what do we have to do? At that time we have to use this expression. So again, we'll start with the most significant bit and divide by 2. So as we move further on the right side, we have to increase the denominator power to square like that, and we go up to 2 to the power of n. Okay, hope it's all right, but let us check with binary, the both cases, with the decimal number. So we'll start with 3 represented in decimal form, and we have to write it in binary form as 1 1, and you can see here 1 into 2 to the power of 1. If you take 2 digits, so 2, n is 2, 2 to the power of 2 minus 1 is 1, and the next one is 2 to the power of 2 minus 2, it's 2 to the power of 0. So this is nothing but 2, and this is 1. So this is the most significant bit multiplied by 2 to the power of 2 minus 1. Okay, and we get 3. So this expression is okay. Now in a fractional case, slightly interesting one. Suppose we want to represent 0.75. What do you have to do? It is represented as 0.11. Why? Because the most significant bit is divided by 2, and the next significant bit is divided by 2 square. What you get from here? And this, when you evaluate, 1 by 2 is 0.5, and 1 by 4 is 0.25, which is nothing but 0.75 in total, same as what we started with. Okay, so the expressions are good. Now we need to do multiplication, jk divided by 2n, and while doing that we need to observe it carefully here. So whenever this jk divided by n can be expressed as 2 to the power of n, okay? At that time, if we get a whole number like 1, 2, 3, it doesn't do anything with the remaining expression, because it just puts 2 pi, 4 pi, 6 pi like that. We know that in circle or in sine wave, it remains in the same place, right? In a circle, you go around 2 pi, you will come back to the same place. So we are not interested in terms with whole numbers, and we are interested only in terms with fractions. Okay, so let us see which one. When we multiply j and k, if we start with k1, when you multiply k1 with each of the factors given in or each of the terms given in j, you will note that all the terms will give a whole number except this one. It's because this is having 2 to the power of 0, and we have 2 to the power of n minus 1, and together they will give 2 to the power of n minus 1. Since we have to divide by 2 to the power of n, we will get a fraction. Okay, what we represented as 0.jn. Okay, this is nothing but 1 by 2. Okay, all right. And when you go to the second term, these two terms now will give fraction. That is why it's written here jn minus 1 and jn. And as we move further, for kn, almost every term will give fraction. That is what is given here. Okay, 0.j1, j2, j3 up to jn. I hope it's clear now. Now, another thing to be noted here is, since j into k divided by 2 to the power of small n is coming as an index to the e, so we know that when we have some addition given in the index, it will become multiplication of two numbers, right? Like when you have 2 square into 2 square, 2 cube, let me say. So this is nothing but 2 to the power of 5. We'll add. So since we have addition, so we need to express this in terms of multiplication, and that is what is done here. Okay. So for every L value, so the L again we are indexing the K. So for every K, you need to take multiples. So that is what is given here. And this sigma k equal to 0 to n minus 1, we can expand it this way. Basically, each k state, k1 to k1, will have some 0 content and 1 content. So that is what we are trying to do here. Now we can take this one outside to make our expression looks easy for implementation. So that is what we are trying to do here. So at that time, what you are doing, multiplication L equals 1 to n, and this, what happens here, you can see when L equal to 1, K1 will be taking, this will be like K1 state, but we know that when we multiply K1, we'll have the first point we'll get is 0.jn. So that is what we are getting here, and like that we can repeat. So and k and we for 0, this whole term will become e to the power 0, which will be 1. So k will be 0. So 0 plus some term coming from this expression. I mean, that will be the coefficient or phase of this state 1. Like that, L equal to 1 to n we need to repeat, and finally you will get a derivative of this one. I mean, you get in the exponent. Okay, so is there any advantage of writing this way? Yes, there is a big advantage. Now we have got a product state, multiplying each one, right, of n 1 qubit states. This is the big advantage. Now we can segregate and they are not entangled. So it becomes easy to handle. Okay. And how to implement as a quantum circuit, let's try to understand. So for that, let's take a simple problem. We have only 1 qubit, we'll assume that way. And let us see how to do, how to get a circuit for this. So this is the expression for 1 qubit. For the time being, we'll forget about this normalizing factor. So I will say that I want to implement a circuit. Okay, so gets 0 to be transformed to gets 0 plus, now if j1 is 0, what happens? So this whole term will become 0, e to the power of 0, which is plus 1. So this will result in ket 1. If it is ket 1, what happens after the transformation? again, and this will be like ket 0 only, whereas this term, what happens, j1 equal to 1 means it is 1 by 2, right? So 1 by 2, that 2 and this 2 will get cancelled. We will get e to the power of pi I, and we know what is e to the power of pi I, that is nothing but minus 1. Okay, so this will become minus 1. Okay, so we have the normalizing factor outside. And we know that we are familiar with this transformation, right? 0 to, this is called plus state, and 1 to minus state. Which gate does this operation or transformation? Hadamard gate. Okay, so Hadamard gate does QFT for a single qubit system. But in general, our problem will be having many qubits, right? So at that time, what we have to do is, let's try to understand what Hadamard gate has done. It has added a phase of pi. Okay, and now as we move further, I can see here, it will be again multiplied by one more 1 by 2, which means we need to keep adding the phase of pi by 2, pi by 4, pi by 6, like that. And that can be done with a rotational gate, a phase gate or rotational gate. And as you can see here, if the problem size is more, the angle to be rotated will be very less. And you can take a decision when to stop depending on the accuracy what you are looking for. Another point to be noted here is we will be adding the phase only when any of the given bits, the original state is 1, right? If it is 0, we don't do anything. So instead of a simple phase gate, we'll be having a controlled phase gate, correct? But another thing to be noted here is, when we started the input state, the J1 is the most significant qubit. But as we start adding rotational gates, you can see this expression now for this expression, this is the most significant qubit. So which is coming in the least significant qubit. So which means we need to do some swapping operation. Okay. So we have to swap like this. The first one to the last one, then next one to the second one, like that. We may be doing n minus 2 swapping. So then we will get exactly this expression. That is, for a given state of qubits, which I've got already the input data encoded, we will be getting state of qubits in some state, okay? And that's what we will see what happens, okay, with an example. All right, so we said it is an efficient way of doing it. How efficient? So first let us understand how many gates we are having to do this transformation. So this is 1, and we'll be doing n minus 1 rotation. So total number for this qubit is n gates. And for the next qubit, we'll be doing n minus 1. Okay, since we are starting from here. Like that, we'll be going, and finally you have 2 and 1. So one Hadamard gate, here one Hadamard and one rotational gate. So we have n plus n minus 1, like that. What is given here? I'm just listing here. I'm sorry. So we have here, which can be expressed as n into n plus 1 by 2. So which shows that the complexity can be expressed as n square. Okay, that is what is given here. And typically the complexity for the best classical FFT is given n into 2 to the power of n. So you can verify it. So we are getting an exponential advantage. See here? I mean, in order to get a feel of it, possibly we'll try with different capital N. So you can see here, as we start from 4, and when we go up to like 1 million, if our size of the problem is 1 million, you have a huge advantage, right? 52,000 times. Okay, I hope you understand the advantage of QFT. We have been calling it as efficient QFT. Then question comes to our mind, is there anything called inefficient QFT? Nobody calls it as inefficient QFT, but people call it with QFT by a single unitary matrix. Again, we'll start from the definition. So if we are able to apply a unitary matrix, again, whether it's unitary or not, you can refer the textbook, what I have given. In fact, the equations given in the previous slide are all taken from Nielsen's book. He has also verified that this matrix is unitary. Okay. So what is this matrix? So it's given as omega n. So the n represents the size of the problem to the power of j and k. So what is first of all, what is omega n? It's nothing but e to the power of 2 pi I divided by capital N. Okay, it's also called root of unity. Okay, so the maximum power, omega to the power equal to 1, we'll say. And how do we fill that? So we have to just put the values. So the rows of the matrix is indexed by j and the columns is indexed by k. Okay, and since we'll start with 0 for j and k, the first element all the elements in the first row and first column will be 1. And how do we fill the next element? So that will be easy. For example, the second row is given by omega to the power of 1, 2, 3, like that. It goes up to n minus 1. And the next row is given it's a multiple of 2, 2, 4, 6, like that. And this will become multiple of 3. Like that, it goes as high as multiples of n minus 1. Okay. So this is how we need to generate the matrix, but we need numbers, correct? So how do we get the numbers in order to do the transformation? So for that, let's take a very simple problem. We assume that our problem size is 4, that is n is equal to 4, and we'll express in terms of omega. So it's easy. We'll try to fill the elements of this unitary matrix. So first row and first column all ones. Afterwards, the first row is easy, omega, omega square, omega cube. And the second row, you should be careful here, and the reason is we have 4. I have written it as 0 because 4 and above, we need to put mod 4. For example, 6 mod 4 is 2. That's why I put 2 here. And similarly, 9. This should have been omega to the power of 9. Instead, I put omega 9 mod 4, which is 1. Okay. So now that we have filled all the elements, but we don't have still digits, numbers to do the matrix multiplication. So for that, what you have to do, as I told you, nth root of unity is the definition. So here it is 4th root of unity, so which can be expressed like omega to the power of 4 equal to 1. We can rearrange 1 to write as omega to the power of 4 minus 1, and we can rewrite omega square plus 1 into omega square minus 1, right? And then further you can go down, and finally when you evaluate, you will get the values of omega with different powers. So as you can see here, omega is I, omega square equal to minus 1, you can get from here, and omega cubed is minus I. And with these values, you can fill it. Now our unitary matrix is ready. We can do all computations. Is there any other way to get these numbers? Yes. what you have to do is you take this circle. This circle is can say from taken from block sphere with the xy plane, and we know that x-axis, and this is a unit circle, right? So it varies from 1 to -1 in x-axis, and the imaginary axis or y-axis, it changes from I to -I. So take this circle, then you segment it. How many segments you have to make depending on the size of the problem. If it is 4, you make 4 segments, and then so 4 segment is very easy. You will get 1. So yeah, omega 0, omega to the power of 0 is 1. Then omega is I, omega square is -1, omega cubed is -I. That is easy to do. Suppose we have 5, okay, n is 5. Then what you have to do? You have to segment it to 5 parts, and for each part we need to calculate omega using this expression. Because we'll be doing 5 segments, right? 2 to the power of, 2 pi by 5. Then we need to calculate, okay, the omega where it intersects the unit circle, okay. So that's how we can also calculate the values to be filled in the unitary matrix. But as you can see here, it's little complex, and for every size of the problem we need to calculate the elements, and then we have to do matrix multiplication. So obviously people prefer the first one, where we just put 2 types of gates: a single qubit Hadamard gate and a 2 qubit controlled phase gate. Okay. Is there any limitation of QFT compared to FFT? Yes, there is a limitation actually. As you know that when we start with the initial state of the qubits after encoding, for example, if we encode 15, which will be represented like 111, right? After the transformation, it will look like this, the state of qubits. And when you make a measurement, it doesn't give the coefficient of it. So that's the biggest drawback of it, right? We can't really find what's happening there. But if you do some more operation, then you get some benefit out of it. So as a standalone QFT, it is having a drawback. Apart from that, we also have another problem of loading the input vector in computation basis. It's not simple and takes time. Of course, this problem is common to all QFT algorithms. Okay, so, but with all that limitation, still it has got a very good advantage in QPE source algorithm. Okay. So now let's see some code running, right? So I have used the code given by Qiskit, okay? So we'll run it in Quantum Lab of IBM. Again, we'll try 2 methods. One method, we will use the function given in Qiskit circuit library called QFT. And another method is building the gates on our own, like Hadamard gate and controlled phase gate, right? And let's start with the simpler one. So I'm creating a QFT circuit for 4 qubits and just calling the QFT. Interestingly, the same function does both Fourier transform and inverse Fourier transform also. Some people call it as QFT dagger. So the only difference it makes here is inverse equal to false, because now we are going to do Fourier transform. Later we will see inverse equal to true and see what happens. Okay. So I built the circuit. Now when I run it, I'm getting the state of qubits. Can't make out anything, right? Does it mean we have not done anything with that? No, we have done. Only thing we need to see how to look at the data. So that's what we'll do in the next example. Okay. So in this, we will build what we'll do. Yeah, we'll build circuit with help of Hadamard gate and controlled phase gate. Then we need to do some swap operation. I mean, a function is defined. Again, this is given in QuizKit documentation. And then later we write our own function QFT, I mean small letter. So we need to call rotation and swap. And I'm going to encode this time 0, 1, 1, 0. That's what I've done here. You can see here this is the rotational part of it, this swap part of it, and then when you look at the state of qubits, you will see, I mean, they are in different states, right? So they are not like no more 0, 1, 1, 0. So this is angle how much, like pi by 2 plus another pi by 4, 3 pi by 2 you can say. This is having minus pi by 2, this is having pi, and this has got 0. Now we need to see how to get that value and try to do some manipulation. Okay. So I also written a code to read out the angle values using again this source code given by IBM. So I'm just trying to extract the data, and then when I run it, I'm getting the angle in degrees like 135 minus 90, 180. You can see here. Yeah, this is 135 plus, and this is minus 90. This is 180, and this is 0. Okay. Now, to this state, if you do the inverse, we are supposed to get our original state of 0, 1, 1, 0, correct? So that's what we'll do. QFT will call, but with this time inverse equal to true, and when you do that, you will get 0, 1, 1, 0. Great. Right, now we know how to do QFT. We know two methods of doing QFT, right? So let me go back. So the references, as you have seen, the QFT given in QuizKit, and of course the Bible. So most of my equations are taken from this reference, right? And I request you to go through the other references given here. In fact, I've given all of them at the bottom of the video under the description. So each one will give some information to you, certainly. I really liked it. So please go through that. And then what next? So you can continue to work on quantum computing. Okay, exploring QFT for more applications or doing it in a different way. Because classical FFT has got many applications. You know that it's being used for image processing, like filtering, then data compression, things like that. So yeah, you can really think over, and you can tell me if you want to do something more on that. I'll do that. Otherwise, I'll come back with videos on QP, quantum phase estimation, and an improved version of source algorithm video. Already I released one, but I want to do something more than that. Alright, thanks for watching it. See you soon. Till then, bye bye.